So folks, in this section we're going to learn a new type of optimization method, and this is called the method of the Lagrange multipliers. The first thing I want to say is just that I feel like this method would be easier for students to remember if instead of calling it the method of Lagrange multipliers in honor of Joseph Lagrange, if we called it instead the method of finding parallel gradient vectors. And so our goal is to be able to use this new method to be able to find extreme values of a function when subject to a constraint. So we need to explain what we mean when we say subject to a constraint. Okay. So just before we get going, the typical problem will look like, the problem will state something like this. Optimize a given function, that's our objective function, but we're going to be restricted by certain constraints. And so the key difference between our new question and the previous max-min questions that we looked at in the last section, where we were just given a surface and then we found the critical points on that surface, and then we found the local maxes and mins and global maxes and mins, is that we're only optimizing our given surface, the points on our surface that lie on some subset of the graph of f. And that what I'm saying is we only want the subset that contains certain x and y coordinates that correspond to some constraint in the domain. So, for example, if we look at this surface right here, z is equal to f of xy, we've got this surface here, and we, in the previous section, learned how to find local maxes and local mins over this entire surface. But instead what we want to do now is we want to restrict ourselves to this pink constraint curve. And we want to ask the question, if we have to stay on this curve that's sitting here in R3, if we have to stay on this curve that's on the surface, where are the global maxes and mins on this subject to this constraint curve if we stay on this curve? And so what we need to keep in mind is that we will always have, for this surface, we will be dealing with a curve of x, y values that lie down in the domain space. Hopefully that gives you a little bit of insight where we're going with this. Okay. So this is how the method's going to work, and we're not going to derive it just now, but this is why I give it the name that I do. I say that I wish we called it, instead of the method of Lagrange multipliers, the method of finding parallel gradient vectors. So here we've got a surface, and our surface in this case is this paraboloid. Some z is equal to f of xy. And we want to find the maximum and minimum values of this surface when we subject ourselves to a certain constraint. Now in this case, our constraint is that our x and y values need to come from this circle down here in the domain space. So this is our constraint. This is our g of x comma y needs to equal 0. That's our constraint curve, and we'll learn how to build that from some given information as we go along. So one thing I'd like to emphasize, folks, is that when I'm talking about the collection of domain values subject to our constraint, in this case, I'm talking about the x, y coordinates in the domain that form this circle. I'm not talking about the closed disk here. We're not talking about the points interior to this circle. I'm just talking about the x, y points on this circle. So the question we ask is, for this collection of xy points in the domain, which of those points, if any, gives us an absolute maximum value on the function, and which of these xy points, if any, gives us the absolute minimum value on the function? So if I were to look at all of the ordered triplets I get by taking, say, here we could take this x naught comma y naught. If we plugged it into the function, that gives us this value right here. That would be x naught, y naught, comma, f of x naught, y naught. That gives us that ordered triplet. And if I took all of those ordered triplets, that would trace out this curve that lies on our surface in R3. And so the questions we're asking is, which of those x, y coordinates in the restricted domain gives us a z coordinate of maximum value? And in this case, I think we can determine it by inspection. It's about, say, right here. Oops, that should be red. It should be about right here in the domain space, because if I take that x, let's give it a name, x1 comma y1. If I take that x1 comma y1 and plug it into our function as an ordered pair, that would give us the ordered pair x1 comma y1 comma f of x1 y1. And just by inspection, you can make the argument that that is the xy ordered pair that gives us the maximum function value on the domain, or on the surface. Likewise, what we also want to find is which of these xy ordered pairs in our restricted domain, and by restricted I mean subject to this constraint, which of these xy ordered pairs gives us a functional value on our surface that is minimal. And in this case, it would be approximately this point right here. Some x, let's call it x2, y2. This point in the domain corresponds to this ordered triplet on the graph of the function, x2, y2, comma, f of x2, y2. And that, just, by inspection, that ordered triplet appears to have the minimum z value on the graph of this surface. So notice, in this case, we're not finding the absolute minimum on the original surface. We're finding the absolute minimum on this surface when we restrict ourselves to only ordered triplets that lie on this, in this case, elliptical curve that lies along our surface, corresponding to these xy coordinates that we restricted ourselves to by our constraint. So the question becomes, how do we find these maximum and minimum values? We can see them here on the graph, but how would we find them computationally? And this is why I call it the method of parallel gradient vectors. If you look over here now, you can see that we've got the contour plot of our f of x, y. So this right here is the contour plot. So there's the contour plot of our f of x, y. That's all of these green level curve lines. But we also have our constraint curve sitting here in the domain space as well. That's the constraint curve g of xy equals 0 shown in blue. And we've said before that our gradient vectors to our original f of xy, that those gradient vectors will always point orthogonal to the level curve lines. So we've done some work to say that the gradient vectors are always orthogonal to our level curve line. So for example, if I went to this point right here, which maybe corresponds to some point back here on the surface, and I said, what's the direction of steepest increase? It would be this direction right here. That is, if we head up that path right there. Okay. So this contour plot, you could imagine as being filled with all of these gradient vectors for our original f of xy. But also, we can find gradient vectors to our constraint curve. So for our constraint curve, we have gradient vectors, and these gradient vectors are always orthogonal to our blue constraint curve. And what do we notice? This is the reason for the name that I give it. That at this point right here, if I were to construct the gradient vector to the function, so this is for the contour plot f of xy, if I were to construct the gradient vector for the function, it would be about this gradient vector right here. And if I were to give the gradient vector for this constraint curve at that same point, what do we see? Well, they may not be the same length. There's nothing that says they have to be the same length, but notice that these two gradient vectors, the black gradient vector from f of xy and the blue gradient vector from our constraint curve, are pointing in the same direction here. And that's precisely where we found a point that corresponded to either a global maximum or a global minimum on our surface when subjected to this constraint. And likewise, you can see that there's only one other place in this contour plot where the blue gradient vectors of our constraint curve are parallel to the black gradient vectors of our contour plot for our original f of xy. Where is that? So pause the video, find that other point where these two vectors are parallel to one another. And so hopefully we found that that point was right here. If I were to construct the gradient vector, maybe it's a short vector right here. If I were to construct the gradient vector for my contour plot at that point, that's where it would be. And if I were to give a gradient vector for my constraint curve, that's where it is. And notice that these two vectors are parallel to one another at this particular point. And there are no other points other than those 2 points where the blue gradient vectors are parallel to the black gradient vectors of the original f of xy. And so these are the points we're going to be looking for. So this gives us some insight for what we're going to do as we work through these problems. What we're going to do is we're going to set the gradient. We're going to set the gradient of f of xy to be parallel to the gradient of g of xy. Well, what does it mean for two vectors to be parallel to one another? What does that mean? Well, it means that one is a scalar multiple of the other. So we'd have some scalar multiplied to the other. So remember that the gradient of f of xy is a vector, or a vector field in this case, and the gradient of g of xy also gives vectors, and we want those two vectors to be parallel, which means I need one to be a scalar multiple of the other. But instead of using the letter A, which is a good choice, or any other letter to show that they're parallel, what we're going to do instead is we're going to use some other letter, and we're going to use the Greek letter lambda. So this is the Greek letter lambda, and it's kind of a cute math thing. Lambda starts with the letter L, and so does the last name of Joseph Lagrange, and that's why we use that symbol lambda, and that's the only reason why we use that symbol lambda in our Lagrange multipliers. So what we're going to do is we're going to take this observation that I want the gradient vectors of my original function to be parallel to the gradient vectors of my constraint function, and we're going to go find the x and y locations that make this statement true together with a constraint. And in the next video, we're going to take that information, we'll review it here, and then we'll go ahead and jump into actually solving some constraint problems. So in the next video, this will be the function that we look at. In this case, this is a hyperbolic paraboloid, and we're going to say if we only take x and y values on that hyperbolic paraboloid that satisfy this statement here, where do we end up with our absolute maximum and absolute minimum values? And we're going to find that using this method of Lagrange multipliers. And if there's one thing I could emphasize, it comes from this idea of setting gradient vectors to be parallel to one another. All right, folks, I'll see you in the next video.